So again, periodic law, chapter 6. And in 1790, Antoine Lavoisier, the first 23 elements. And then in 1864, John Newland's first proposed organizational scheme for the elements. So Lavoisier was a very interesting person. He had a lot of very important discoveries, but one of his more poorer discoveries was he actually believed that heat was an element. He actually had a symbol for it. It was before they had the symbol Ca. He called it caloric, which is actually where the word calorie comes from. So he believed that when things heated up, they were interacting with an element called caloric. Turned out a gentleman from Germany proved him wrong. What the guy did in Germany is he actually made cannons of all things. And he noted that whenever he drilled the bore in the cannon, no matter how long he drilled it, the water kept on getting hotter and hotter. And he thought there's no way there could be that much element just kept on coming in. And he actually ended up proving Lavoisier wrong. The reason I tell you that story is because this is Lavoisier's wife, Madame Lavoisier. Now, if you look at 1743 to 1794, do we know what was happening in the mid-1790s in France? Yeah, he lost his head. Guillotine. Her head was going to be lost too, but she managed to get across the border to Germany, where she met the German gentleman who had proved him wrong about caloric, and she married him. So she married his nemesis. Dang, yeah, huh? That's pretty sketchy, huh? Right? Okay. So here we go. Dmitri Mendeleev. In the middle 1870s, he was a Russian chemist who first developed the periodic table. Actually, he was a high school chemistry teacher in Russia. And he basically took a lot of the data that had been floating around, he put them on these little cards, and he started trying to organize them. And he actually kind of came up with the first sort of draft, if you will, of a periodic table. In fact, last year I did that activity. This year I do this one on this page, and Mr. Moylan did it with their classes. They did the periodic, it's called the periodic card sort. So he looked at different properties, their masses, and he tried to align them. Okay? And so what happened was, this was his first periodic table that he proposed. Now this was actually, he did it in Russian, but then he went to Germany. He went to Germany, and this was actually published in a German journal. Gruppe is the German word for group. So you see he has some groups. And the interesting thing about Mendeleev is that he actually left blanks in the periodic table. And what he said was, based on my analysis, we're going to discover an element with a mass of 68, and it's going to have such and such and such properties. And it turned out he did. He was right. And so over the next 10 years, many of these ones where there were blanks were discovered exactly where he said they would be. So people said, hey, this guy's onto something, because he's able to predict elements before we find them. That's pretty cool. Okay? And in fact, this table actually led to people looking for those elements. So it actually spurred more elements being discovered. Okay? So what I need you to really take notes on those right here. Mendeleev's periodic table was based on increasing atomic mass. So his table was somewhat slightly different from today's table. He didn't quite get it right. He probably got it about 85 to 90% right. Okay? But keep in mind, he did this in 1872. That was a full 25 years before the electron was discovered. How many? 50 years before the proton was discovered, or 40 years before the proton was discovered. No idea really of an atom or of subatomic particles or any of that stuff. People, as they moved on, once they learned about those things, they modified the table slightly. Here's actually a first draft. Here's the actual first draft version of Mendeleev's table. I believe it's in a museum in Russia someplace. It's worth a lot of money. Some people say it's the first periodic table ever. Okay? So anyways, so he's pretty much given credit for the discovery or the production of the first periodic table. So, but then in 1913, this fellow Henry Moseley, he was conducting X-ray experiments on elements. Guess who he worked for in 1913? Any guesses who he worked for? Yes, he worked for Ernest Rutherford. In fact, 1913, what was the gold foil? Was 1911, 1912. So he was there working on this stuff. Okay. And as part of his research work, he actually was the person to introduce the idea of the atomic number. In other words, let's give each element a number based on their protons. He said, I think protons are important. Okay? Protons are important. And sort of the outcome of this is when he looked at the atomic number and he went back and looked at the periodic table that they were looking at, Mendeleev's table, he made a slight adjustment. What he did is he found that if you took Mendeleev's table and ordered it by atomic number instead of atomic mass, there had been some inconsistencies in Mendeleev's table that went away. Some elements weren't quite in the right place. It turns out that because of isotopes, some elements that are earlier have lower atomic masses than ones that are in front of it. And actually, once they ordered it by atomic number, much of this was eliminated. And basically, once this table came out, this essentially is the periodic table you see today, with added elements that were discovered since 1913. Okay, but so essentially, it's Moseley's table. However, Mendeleev is given credit, rightfully so, because he was the first person to really put these into a meaningful organization. So again, this is the blueprint for the modern periodic table. So in a test, this becomes an issue because atomic mass, atomic number, Moseley, Mendeleev, and they both start. So you got to get that straight in your head. Moseley, atomic number, Mendeleev, atomic mass. Okay, lots of students gets these mixed up. Okay. And a lot of times the question is really simple. It says the modern periodic table is organized by, and it says number of neutrons, atomic number, atomic mass, average atomic mass, and the answer is atomic number. So those types of things, okay? Because we got about 10. Oh, we might be able to get it done. I'm a little bit behind. And there's Moseley. That is his, believe it or not, his X-ray camera. Here, let me take your picture. X-ray camera. Think about that. Had a camera that produced X-rays, and he would just take pictures. Could you imagine? He's holding it. Hey, let me snap a shot. Let's see what your X-ray looks like of your face. Crazy, huh? Didn't really know. I don't think they appreciated the dangers of X-rays back then. That's what I'm thinking. Okay. So, a couple of, unfortunately, go for it. Write these down. If you think you can understand them, go ahead. But periodic law is the physical and chemical properties of the elements are periodic functions of their atomic numbers. So that was sort of the answer to today's warm-up. Why is it the periodic table? Because it turns out that the physical and chemical properties, this is kind of what Sasha said, are periodic functions of their atomic numbers. That's why the periodic table ends up shaped like that, because we're trying to put these things in groups. Okay? And so the consequence of that is a periodic table. Okay? The consequence of that is a periodic table where the elements are put in order of their atomic numbers, and then they're ordered so that the elements with similar properties fall into the same group. There's 18 groups, people. 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to the noble gases, 18. I like to call them, I like to focus on take the transition metals or the D block out. I like to focus on group 1, 2, and then I like to call group 13, 3, group 14, 4. I call them 1A, 2A, 3A, 4A, 5A, up to 8A. We'll talk more about why that is. Okay? So go ahead and write those down. Okay. You guys ready? No. Only got 9 minutes. We still got to do periodic table geography. Where's Alondra? How far are you, Alondra? Similar properties? Oh, you're almost done then. Fall in the same group. Okay. Moving on. Oh, I see Tails racing. Good. Okay, let's do it. Okay, so The periodic law leads to something known as periodic trends. It turns out that we can look at the periodic table sometimes not as individual elements, but look at the whole thing together. It's a big sort of rectangle, and how do trends occur. So one trend that we're just going to talk about today, then on Friday or Monday we'll talk about the rest of the trends. But I'm just going to bring this one up. It's called atomic radii. And all atomic radii means is it's just the size of an atom relative to each other. It's just the radius rather than the diameter. Okay? And they actually calculate the radii of the atoms by taking two atoms, putting them together, and then they're trying to calculate x there. So they get this 2x and they divide it by 2. So they do these measurements. Okay? And so they can get different sizes. And it turns out that where you are on the periodic table can actually tell you how big you are. So you don't even have to know anything. You can make predictions about the size of atoms. So, first of all, would we all agree which is bigger, hydrogen or francium? Francium. So you just why does someone say that? Anybody? Why? Go for it, Jared.
It has a larger atomic number and a larger atomic mass.
Yeah, it's got a larger atomic number, bigger nucleus, and so it has all those electrons in the shells. Remember the 6s orbital, the 5s, they're big circles. They're getting bigger and bigger and bigger, so they're further away. So more stuff, it gets bigger. Okay? So now, if this is the biggest one, could we make any predictions about what the smallest element might be? What if I told you that we find out that rubidium is bigger than strontium, is bigger than yttrium, is bigger than zirconium? Which is the smallest element? Helium. Yep, helium is the smallest element. Over here. Look at the symmetry. Largest in this part here. Largest, smallest. Okay? So there's a picture of it, kind of minus the transition metals. This doesn't go to francium, but it goes to cesium. You see how big cesium is, and you see how small helium is. Okay? So there's another trend. It seems as though they get a little bit smaller as you go across a period. So there's all sorts of trends like this. There's things called ionization energy, which is a question in your lab, right? And there's electronegativity, there's size of the ions, and it turns out a lot of these you can pretty much, once you know one, you can kind of go, oh, it gets bigger this way, or they get smaller this way, okay? So this is just one of them, okay? Periodic trends, the size of an atom. We'll talk more about that later on, okay? So I think I'll go ahead, and I'll just leave this up for you. I won't describe it. I'll just let you take notes on this. This is about the rationale of why atoms get smaller as you go across a period. Let you guys think about that. Due to added positive charge in the nucleus. Think about what electrons do when they see more positive charge. They're attracted to it. So they kind of get sucked in a little bit. Okay? Okay? So we're going to talk more trends. So now we have to do periodic table geography. You guys ready? No? No periodic table geography? Oh. But we got 4 minutes. That's like plenty of time to do it. Might as well get it done. Okay? Ready? Here we go. Don't take those notes. Periodic table geography. Okay? So, everybody together. The horizontal rows of the periodic table are called periods. Okay, let's do that again. The horizontal rows of the periodic table are called periods. Let's do it one more time. The horizontal rows of the periodic table are called periods. Yeah. You know why teachers do that? There's some research that says if you say something like that 3 times, you learn it more. I don't know if it's true or not. Okay. But I do know that every year, this question and the next one, so let's do this one. The vertical columns of the periodic table are called groups or families. Let's just do groups this time. The vertical columns of the periodic table are called groups. The vertical columns of the periodic table are called groups. Believe it or not, I get about 6 or 7 students every year in my 4 classes that get those wrong. They get 2 off on a test because they get them mixed up. Don't be that person. Don't be that person. And again, elements in any group of the periodic table have similar physical and chemical properties. Okay, next. Alkali metals. Say that, everyone. Alkali metals. Alkali metals. What's the next one? Alkaline earth. Ready? Say it. 1, 2, 3. Alkaline earth. Very good. What block do the alkaline earth metals make up? The S block. The S block. Right? S block. These 2 right here. Okay. You guys got that? Alkaline earth. Next. The D block, or the transition metals. We call that the D block, right? Oh no. Oh, well, we'll just go to this. After the D block, we call these the inner transition metals. I'll give you another name. Okay, 1, 2, 3. And then I'm going to say what it is, and then you'll do it. So rare earth metals. Okay, 1, 2, 3. Rare earth metals. Yeah, 1, 2, 3. Rare earth metals. Yes, these are the rare earth metals. China owns about 99% of the world's supply of the rare earth metals. Believe it or not, every one of your iPhones has rare earth metals in them. Okay? Oh, there it is right there. Okay. Next, the halogens. Everyone ready? Halogens. Halo, yeah. Say it again. 1, 2, 3. Halogens. Halogens. And here's the last one we're going to do. Noble gases. Why are they called the noble gases? Everyone wants to be like this because they don't react with anything. Turns out that's not true. In the 1960s, some chemists discovered that you can take xenon and react it with one of the most reactive elements, fluorine, and they actually can make XEF compounds. Very hard to do. So they're not quite noble. Okay? Pretty much, though. And that is it. You guys got about 1 minute, 30 seconds. Pack up your bags and don't leave until the bell rings. In bar, and you guys just hang out, and then I'll give you the homework. Yes, for you guys. I keep on thinking you. I mean, Sasha in the bar. Keep on. That's due next Thursday, October 3rd. Oh, you as well? Just tomorrow? It's number 44.
Were you taking the apple, right? I'm like, okay. No, I didn't have an algebra.
You know what? You don't need
I was like, you need to go.
You just hang out and I'll print you out a cover sheet. It's like a mineral. I gotta take care of you. Okay, in bar, Sasha.
Fair amount of work.
Should I do this? See through the door there? There's a cart right on the other side of the door there. Okay, so look at these posts. Team Curly gave us homework. Table. Lift it. Okay. Periodic table. Don't lose the periodic table. And then 45 is the assignment we're doing on Monday, right? Have it for your Monday. Yeah. Goodbye. Okay. Yep. Anybody else? Okay, what? Nothing. Good. Wait. Do it fast. No, you're fine. Don't worry about it. Okay. So, cover sheet.
Okay. I'll wait.
It's just easier to print that out and try to.
All right.
Thanks, Brett.